Now we have gotten to a point in our study of functions where we are going to use the tools that we have learned in the previous sections to collect information about a given function so that at the end we can sketch its graph. The type of information that I am talking about, it's related to first finding simple things about the graph, such as domain and range, asymptotes, intercepts, and then putting into practice the new tools that calculus has given us. Tools such as evaluating limits at positive or negative infinity to find horizontal asymptotes, finding the first derivative of the graph so that we can find critical points, do the first derivative test for local extrema, finding the second derivative of the function so that we can talk about the concavity of the graph, find possible points of inflection. And then when we put all that together, we should be able to draw quite an accurate graph of the function. So this is the goal in this section. The goal is now to gather all this information about a given function in order to sketch its graph. You can see right here that I have created a set of guidelines that you can pretty much always follow when trying to gather information about a function in order to sketch the graph. One of the first few things that I like to do is to find the domain of the function, the intercepts, vertical asymptotes, horizontal asymptotes. It is here actually where calculus begins, because it is here where we have to evaluate limits at positive or negative infinity. And then with 5, the first derivative test. That will help us find local extrema, talk about increasing, decreasing intervals, and so forth. And then 6, the second derivative test, which will allow us to talk about the intervals where the function is concave up, concave down. So anything related to concavity, but also possible points of inflection. Then I like to sketch the graph. And when I sketch the graph, then that's when I like to talk about the range. I like to leave the range until the very end, because once I have a graph in front of me, I find that the range becomes pretty much obvious. And because order doesn't really matter in terms of the range, it is totally okay to leave it until the very end. In this video, I will consider 2 functions and I will try to sketch their graphs. And you're going to see that in both cases, I am going to be following these steps right here. Over the years, I have found that this particular order works very nicely and is very effective. At the end, I gather all the information that I need to be able to sketch the graph. So feel free to have these steps, these guidelines right in front of you as you follow my discussion in example 1 and example 2. Example 1 is asking us to do a complete differential analysis on the following functions in order to obtain an accurate graph. The first function is f of x equals 6x squared minus 6 over x to the third. I'm going to go ahead and follow the steps from the guidelines one at a time. Now, we are going to need the first derivative and the second derivative. But in order to save a little bit of time here, I will assume that you feel comfortable using the quotient rule to differentiate f of x and then f prime of x to get the second derivative. So I'm just going to go ahead then and give you right now those derivatives. Here they are. And we're just going to go ahead and use them as we go through the solution. So you notice that here is f of x, here is f prime, and here is the second derivative, f double prime. Let's begin with step 1, finding the domain. Notice that for the domain of the function, again, let's always remember the goal. The goal is to sketch the graph of f of x. We are not sketching f prime. We are not sketching f double prime. We're using f prime and f double prime for finding information about f. But the goal is to sketch f. So what is the domain of f? The domain of f, depends completely on this denominator. See, f of x is a quotient. It has a numerator and denominator. So then we know that the denominator cannot be equal to 0 because division by 0 is undefined. So immediately, the domain of the function will consist of all values from negative infinity to 0, but excluding 0, and then union 0 to positive infinity. So that is the domain of my function. Now that I have the domain, I'm going to go on and talk about the vertical asymptotes, if it exists. I'm going to use V dot A as an abbreviation for vertical asymptotes. The vertical asymptotes, again, they usually come from the denominator. If the denominator equals to 0 at a value of x, it is there where you have a vertical asymptote. And we notice that because x equals 0 will make my denominator 0, then x equals 0 will be a vertical asymptote for my function f of x. So then vertical asymptotes, x equals 0. Now, when I have a vertical asymptote, I always like to analyze the asymptotic behavior. In other words, I like to analyze the behavior of the graph around the vertical asymptote. I know that around the vertical asymptote, my function is going to have an infinite behavior. It will either tend to positive infinity or negative infinity, and I would like to figure that out before I get to the sketch. So the way that I do that is I draw just a rough sketch like this, very, very rough. X equals 0 is the vertical asymptote, so I'm going to highlight the y-axis in blue like this. X equals 0 is the vertical asymptote. And I want to know, as x approaches 0 from the left, where are the y values going towards? And as x approaches 0 from the right, again, where are the y values going towards? And the way that I can do that is by just looking at the function. Let me write the function here again. F of x equals 6x squared minus 6. Let me factor 6 out and write it as x squared minus 1 divided by x to the third. This is the function that it was given to me. So now let's see what happens. Let's do as x approaches 0 from the left first. Let's come towards the asymptote from the left in this direction like this. Whenever you're doing your asymptotic behavior, you're going to choose a test point, a point that is on the left of 0. But you want to keep that point pretty close to the vertical asymptote because you want to make sure that you obtain accurate information. And that means that whatever test point you choose should be very close to the y-axis. I feel that -1 is too far. Let's choose something like -1/2. If I plug in -1/2 here in place of x and -1/2 here as well in place of x, my numerator, I only care about the sign. I don't care about the actual number. I just want to know whether it is going to go to positive or negative infinity. So again, if I plug in -1/2 for x, the numerator will be -1/2 squared minus 1. That is going to give me, this quantity here will be negative. The denominator will also be negative. And now, a negative number divided by a negative number is a positive number. So then I know that my graph will go towards positive infinity. Now, I am going to choose a test point to the right of 0. Again, a point that remains very close to the vertical asymptote. So +1/2. And then when I plug in +1/2 for x here and x here, I am going to get in the numerator 1/2 squared minus 1, which is going to be negative. I will do that in yellow. And then in the denominator, I am going to have 1/2 to the third. That's going to be positive. Now I know that a negative over a positive is a negative. So then my graph is going to approach the vertical asymptote and it's going to go down towards negative infinity. So this is already something that I know about my graph around the vertical asymptote. So in proper limit notation, this is saying that the limit as x approaches 0 from the left of my function f of x will be positive infinity. And the limit as x approaches 0 from the right of f of x will be equal to negative infinity. So something now that we're going to keep in mind when it's time to sketch. Now, why don't we find the x-intercept and the y-intercept? Please know that sometimes I am going to mix the order of the vertical asymptote and the x-intercepts from the official guideline that I gave you a few minutes ago. That's totally okay. Sometimes I confuse them. I find the asymptotes first and then the intercepts. Sometimes I do the intercepts and then the vertical asymptotes. It doesn't matter as long as you follow those steps all the time. All right, so continuing, let's go ahead now and do the x-intercepts. We need to know that. So 3, I want to find the x-intercepts. In order to do that, I am going to let y be 0. So then that means that we're going to take the function 6x squared minus 6 over x to the third, and we're going to set it equal to 0. You will cross multiply, and you're going to have that 6x squared minus 6 will be equal to 0. So 6x squared is going to be equal to 6. X squared is going to be equal to 1. X will be equal to plus or minus 1. That means that we found two x-intercepts, negative 1, 0, and we found 1, 0 as the intercepts, the x-intercepts. Now we're going to go ahead and find the y-intercept. In order to find the y-intercept, we know that we have to let x be 0. But then that becomes a problem because 0 is not in the domain of the function. We have a vertical asymptote at 0. So then that means that there are no y-intercepts. So I'm going to say over here, none whatsoever. Step number 5, I think that at this point, we are ready for critical points. I'm going to use CP as an abbreviation to save a little bit of time. Critical points. Critical points happen in two ways. They happen when the derivative at the values of x, where the derivative is equal to 0, or when the derivative is undefined. Okay, so let's do case number 1, when the derivative is equal to 0. So the derivative is equal to 0. Now here is the derivative, exactly when the numerator is 0. So then that means when negative 6 times x squared minus 3 equals 0. Meaning when x squared minus 3 is equal to 0, when x squared is equal to 3, when x is equal to plus or minus square root of 3. Then for the second case, when f prime of x is undefined. F prime of x is undefined exactly when the denominator is equal to 0. So then that means when x to the fourth is equal to 0. In other words, when x is equal to 0. So we seem to have 3 possible critical points. And I want to emphasize the word possible. These are possible critical points at the moment. In order to make them official, I have to make sure that these 3 points are in the domain of my function. I want to make sure that f of those points, f is defined at those points. F is defined at plus or minus root 3, but f is not defined at 0. In fact, 0 is not in the domain of the function. So then that means that 0 is not going to be an official critical point. So we're going to say here that since x equals 0 is not in the domain of f of the function, not of the derivative, of the function, then the only critical points are x equals plus or minus square root of 3. These are the only critical points. So this is where I hope to obtain a local maximum or a local minimum. We're going to go ahead and do that by doing the first derivative test. Before I do the second derivative test, however, I just realized that I forgot to do the analysis on the horizontal asymptote. In fact, that should have been part of number 2. I did the vertical asymptote there, and I was supposed to also do the horizontal asymptote. So you know what? Let's go ahead and do it now. It doesn't matter. So I'm going to go ahead and put a red arrow indicating that it should have been part of this segment right there. So doing the horizontal asymptote. For the horizontal asymptote, we have to try to evaluate the limit of the function at positive and negative infinity. So we're going to try to see, well, what is the limit as x approaches plus or minus infinity of the function 6x squared minus 6 divided by x to the third. Now, this function is a rational function. We have a polynomial over a polynomial. So you need to remember from one of the sections in the limits chapter, that the way that we evaluate the limit of a rational function is to consider, let's say, the leading coefficient. I'm going to bring it in front of the limit, and I'm going to have 6 times the limit as x approaches plus or minus infinity of just the ratio of the leading variables on top and below. So this will be here the limit as x goes to positive or negative infinity of x squared divided by x to the third. So that is going to be equal to 6 times the limit as x goes to positive or negative infinity of x to the negative 1, which is going to be 6 times the limit as x goes to positive or negative infinity of 1 divided by x. And I want you to notice that now when you consider this limit as x goes to positive or negative infinity of 1 over x, if x is getting very, very large, positive or negative, then 1 over something very, very large is very, very small. So 1 over x is going to be approaching 0. So that means that we're going to have 6 times 0, and that's going to be 0. So our conclusion is that the line y equals 0, in other words, the x-axis is a horizontal asymptote. So now we are ready to continue with the second derivative. Now we're going to start doing the first derivative test so that we can find intervals of increase, decrease, and so that we can determine whether we're going to have local max or local min at root 3 and root 3. If you notice, I have plotted negative root 3 and root 3 there. I am going to put a closed dot on top of these radicals. And the closed dot is telling me that my derivative is 0 there. I am also going to put an open circle on 0. And the open circle is needed there because if you remember, 0 is not part of my domain. This is where I have a vertical asymptote. Now that we have our derivatives figured out, we can tell whether we're going to have a local max or a local min at the two critical points. Let's look at the signs of the derivative. Let's go from left over here to right. The derivative changes from negative to positive. So then that means that we are going to have over there a local minimum, just like this. And then let's see what happens on the left of positive root 3. On the left of positive root 3, the derivative goes from positive to negative. So then that means that we're going to have a local maximum. So now I can say that f has a local minimum at x equals negative square root of 3. And f has a local maximum at x equals positive square root of 3. So that's what we have. Now let's move on to the second derivative so that we can start analyzing it for information in regards to the concavity of the graph and possible points of inflection. We can begin with the possible points of inflection. So for points of inflection, these are the following conditions that have to be satisfied. We need for the second derivative of x to be equal to 0 at a value of x, or we need the second derivative of x to be undefined. Actually, even though I said or, it should really be and or, because it can happen in both cases. So let me even put over here and as well. These are the two conditions that we need to consider. So number one, when is the second derivative equal to 0? And in case you missed it, I copied over here the second derivative just to have it here in front of us. So the second derivative is equal to 0 when the numerator is 0. That means when 12x squared minus 6 is equal to 0. In other words, when x squared minus 6 equals 0, which implies that x squared is equal to 6, meaning that x equals to plus or minus square root of 6. So that's a possibility. Now for the second one is when will the second derivative be undefined? It is undefined when the denominator is equal to 0. That means when x to the fifth equals 0, which implies when x equals 0. So what I have so far are the three possible points of inflection. And I'm emphasizing the word possible because I have to check two things for them to be official. Number one, the initial function f has to be continuous at 0 and plus or minus root 6. And number two, concavity has to change around these 3 points. There is one point that we can eliminate right now. And this is the point x equals 0 is eliminated because the function is discontinuous at 0. So therefore, it fails the condition of the theorem for points of inflection. Then the only two candidates that remain are plus or minus root 6. But right now, they're candidates. I'm going to have to check concavity. But I'm going to make the statement right now that we are eliminating x equals 0. So we're going to say that since f is discontinuous at x equals 0, then f does not have a point of inflection there. Okay? It doesn't. That we know for sure. All right. So now let's move then on to concavity. And in order to do concavity, in order to analyze concavity, we're going to do something very similar to the first derivative. We're going to draw a number line. we're going to have now the second derivative here, and we're going to do test points to be able to determine the concavity. Again, we have 4 intervals here that we're going to have to analyze. This interval on the left, this one here, this one, and the far right. We're going to choose our test points. Negative root 6 is approximately negative 2.4. Negative 2.4. So we're going to choose something like negative 3. So if I plug in negative 3 for x here on top and below, I am going to have negative 3 squared is 9. 9 minus 6 is positive. Negative 3 to the 5th is going to be negative. A positive over a negative is negative. So when my second derivative is negative, let's say when f double prime of x is less than 0, then I know that my graph is going to be concave down in that interval. Now let's choose something like negative 1 between 0 and negative root 6. So let me erase again these signs right here. And if we plug in negative 1 in place of x, and let's say we plug in negative 1 in place of this x below, so on top and below negative 1, we're going to have negative 1 squared, which is 1, minus 6, that's going to give us negative 5. So then that's going to be negative here, and then we're going to have another negative here. We know that a negative over a negative happens to be positive. So I'm going to have positive throughout this interval. That's telling me that the second derivative of x is bigger than 0. So then my graph is going to be concave up in that interval. Similarly here, we're going to go ahead and choose now positive 1 as our test points. So erasing again with positive 1, we're going to have 1 minus 6, that is going to be negative 5. So then that's going to give us negative on top, and then positive 1 to the 5th is going to be positive. So a negative over a positive is going to be negative. Again, my second derivative is going to be negative in that interval. So f double prime of x will be less than 0. That means that my graph is going to be concave down in that interval. Now we're going to go here and choose a number like 3. If we plug in, erasing this again, if we plug in 3 on top and 3 below, we are going to have 3 squared, which is 9, minus 6. That's going to be positive. That's going to be a positive. A positive over a positive is positive. So my graph is going to be concave up in that interval. So now I know I can state the concavity of my graph. So I will say that f is concave up in the interval from negative root 6 to 0, and then root 6 to positive infinity. We will say that f is concave down in the interval from negative infinity to negative root 6, and then 0 to the square root of 6. And then I notice that concavity changes at the possible points of inflection. At negative root 6 and positive root 6, we have a change in concavity. So then this is telling us that exactly at these points right here, the function is going to have points of inflection. So we can say nicely that f indeed will have points of inflection at x equals plus and minus 6. So we're going to see there how the concavity is going to change when we actually sketch the graph. You can see that right here, I have calculated the y values for all of the important points that we found in the previous analysis for the local max and local min, and the 2 inflection points. I've also stated the x-intercepts. And the way that I found these y values is by going back to the original function. In other words, you take root 3 and you substitute it into the original function, you do the algebra, and you get the value for y. So when x is root 3, the y value is approximately 2.3. And I rounded just because I need to sketch. So it's easier to work with decimals whenever sketching a graph. So what I'm going to do now is I'm going to go ahead and plot all of those points as accurately as I possibly can. The first one are going to be the x-intercepts. That's going to be at 1, 0, negative 1, 0. And then we are going to have nicely the point root 3, which is precisely when x equals to 1.7, let's say somewhere here. And then the y value is going to be 2.3. So let's approximate that to be somewhere here, for example. So I'm going to put a dot right there. Then in the other case, we're going to have negative root 3. So negative 1.7, let's say somewhere there. And then the y value is negative 2.3. So then let's say somewhere here. Again, approximating. Then we're going to have the inflection points. I'm going to put those points in red. So root 6 is approximately, we said that root 6 was approximately 2.4. So 2.4, let's say somewhere here, the y value is going to be approximately 2.04. So that's going to be a little bit closer over here to 2. Let me put it right there. Then we're going to go to negative 2.4. So somewhere here. And then the y value will be negative 2.04. So negative 2.04. So let's say somewhere here. Again, close to negative 2. So these red points are my points of inflection. Now, if you want, this is a good idea to go back to the number lines that we drew for the first derivative, because that will remind us of the intervals of increase and decrease, and also to the number line with the second derivative, because that will help us with the concavity of the graph. I remember that on this part over here, the graph was concave up and then it shifted to concave down at the red point of inflection. And then there is a local minimum over here at this black point. So I think that I can start sketching my graph. So the sketch is going to go like this, concave up to this point. Then the concavity is going to change slightly. Try to be as smooth as possible. We're going to reach to a minimum value here, and then we're going to go down like that. And then the graph continues increasing, and we know that we're going to get to positive infinity because the y-axis was always a vertical asymptote. Then on this part over here, again, revisiting the number lines from before, we're coming from negative infinity. We're going to go through there, and this is the place of that the graph is concave down. Then we reach a local maximum here. We continue concave down, but then here we change the concavity, and now the graph continues like this forever. Since the x-axis is a horizontal asymptote and the y-axis is a vertical asymptote, I also want to make that very obvious in my graph. So typically what you're going to do is the following. You're going to go ahead and with a straight edge, you're going to trace through the axis with a dotted or a broken line. And this is pretty much the norm in calculus. This is the way in which we show that this particular line is a vertical asymptote. I'm going to also label the line as x equals 0 to make it super obvious. And then I'm going to do exactly the same thing here with the x-axis. I am going to draw it or somehow trace it. Let me go a little bit more above here. I am going to trace it with a broken or a dotted line in this direction. So this is really showing that the horizontal axis, the line y equals 0, is a horizontal asymptote. So now I think that I have captured all important elements of my function, and I have shown that in my sketch right here. Now we have a pretty accurate sketch of the original function. And as a result, I can determine the range of the function. So now I notice that this function over here in this direction covers all positive y values, starting from this low y value here. And then the other branch of the graph captures all of the negative y values. Remember that this graph continues down like this towards negative infinity. So pretty much all y values are captured in this graph. That is telling me that the range will consist of all real numbers from negative infinity all the way to positive infinity.